Good evening and welcome everyone. Hope I am audible and my screen is visible. Welcome to the problem solving session of the course Microwave Engineering. Uh, can you just confirm I am audible once again? Can you please?
Yes, ma'am, you are audible and your screen is visible.
Hello.
Hello, hello, hello.
Can you please type in the chat? I think there is an issue with the audio. I'll just try to figure it out. Hello.
Hello,
Yeah. So thank you,
hello.
thank you. Actually, I was not able to hear you. So thank you.
Okay, okay.
So yeah, let me introduce myself. I'm Susan, a PhD scholar at Electrical Engineering Department of IIT Madras. So, as you know, there will be an interactive session for the problem solving every week for this course. Basically, there will be two sessions. One will be on Friday, which 6 p.m. to 8 p.m., and another on Sunday. So Friday sessions will be handled by me. And as you all know, this is a 12-week course, and we will have basically 12 sessions parallel to the weeks. And we'll be discussing every week the weekly content in a brief and try to solve numericals which are similar to our assignment questions or which will help you to attain the assignments better. So I am planning to start today's session with a short introduction, and probably I would really appreciate if you could just unmute yourself and introduce yourself. That will be great. We could better interact. If because we have just 7 members, probably it is nice if we could interact.
Hello. I am audible, ma'am.
Yes.
Myself Anup Pandey, ma'am, and I am pursuing MSc Electronics from Jamia Millia Islamia, New Delhi. Before
Okay.
that, I have completed my BSc Honors Electronics from Delhi University.
Okay. Thank you, Anup.
Okay, welcome.
Hello, madam.
Hi, Arun.
Yes, ma'am. I am Arun Raj. Uh, I am working as an assistant professor in Visum Engineering College in Andhra Pradesh, madam.
Okay.
Department of ECE.
Okay, thank you.
Good evening.
Good evening, ma'am.
Good evening. I'm Suvarna Kadam, and I'm working as an assistant professor in Pimpri Chinchwad College of Engineering, Pune. And I'm pursuing my PhD from the University of Johannesburg, South Africa.
Okay,
So,
nice.
as there is a like I have taught this subject for many times, but as the contents are very catchy for the last sessions,
Okay.
and it is the topic of my research also because I am working in the wave IC design
Wow,
there.
nice.
So that's why I joined this session.
Okay,
Thank you.
thank you. So Anup has to say something. I think he has.
Hello, ma'am. Actually, I am working on slow wave structures, and so I want to uh, I want to make a slow wave structure using metamaterial so that if any reflected wave or any reflected waves coming towards, then I want to suppress the reflected waves.
Okay,
So
okay. So I
yeah,
understand
yes,
slow
ma'am.
wave structures, right?
Yeah, yes, ma'am. Yes,
Okay,
ma'am.
okay, okay, okay. Yeah. Okay, thank you. Thank you, Anup, for the comment. Anybody else want to introduce themselves? Yeah, okay. I think we will just try to start our session. So, in fact, I wanted to give an introduction to the course in general because this course is giving some basically giving some fundamental and intended at some audience who like to learn very basics of microwave engineering. And I must say, in addition to that, uh, we would like to we will be able to learn some of the applications of this microwave in communication and other subsequent areas. And at the same time, there are some basic circuits and subsystems which we will come across, both passive and active microwave circuits, towards the end of this course. So, the beginning of the course will be basically focused on the very fundamentals of transmission lines, which is really helpful because almost all the application areas require the knowledge of transmission lines. So that is going to be the very first part of this course. So in today's session, okay, before moving on to the session in detail, I would like to quote these are some of the books and references. These are available. I mean, the list is already available in the website of NPTEL. The professor had given these references. So these are some of the very our references are need not be just limited to this, but these are very nice books wherein we can find really good explanations and fundamentals of this microwave engineering. So actually, I thought of asking every learners, why are you interested in this course, so that I can know you better and interact with you all better. So I think we already interacted before. So I think some of you are a faculty in engineering college, and some of you are PhD scholars as well. And I suppose most of you are interested in this course, particularly for some reasons. So probably I request everyone to have this be an interactive session so that it help both of us, because one side interaction might not help, or I might not understand if something is missing. So I would like to request you, if you have any queries or any questions, please ask in between. Please stop me and ask in between. So just a introduction question. Just you can all just type in the text or chat box. What do you think, or maybe you all know, what is the frequency range used by the telecom operators in India for this 4G LTE band? I'm quite sure all of you know about the 4G band which we use in our phones. So any idea of what is the range of frequency which is used by this particular 4G band? I mean, the most of the telecom operators have almost the same band. So I have given you some options. Just think, just type in your answers. What do you think is the frequency range? So this is basically an MCQ. You can have A, B, C options. So it's not a numerical question, so you can always answer. I request everyone to answer this, either A, B, or C. Yes. So as most of you said, it is B, option B. So the frequency range used by most of the telecom operators in the 4G band is 2.3 to 2.4 gigahertz. So as most of you work on something like antennas, you probably might know what is the frequency ranges which we focus on. So to give a short introduction to the microwave frequency bands given by the IEEE definition. So these are the different bands as we see, L band, S band, C band. So as you see, these microwaves, and there is millimeter waves right now, which is basically 30 to 300 gigahertz. And so the radar frequency bands was a very first reason for getting these different bands with the name L, S, C, X, etc. So basically, these are all used as initially the very first applications of microwave engineering was in radars. So there we have this different bands of operation in the military application on the defense field. So as you see, this 1 to 2 gigahertz is L band, or S band is 2 to 4 gigahertz, which is really very common these most of the times. And C and X band are most of the bands which is being used for the waveguides as such, which we will definitely come across in the upcoming lectures and video sessions. So first I would like to start with our assignment 0. There were some prerequisite based questions so that you will get accustomed to this particular course. So the prerequisite for this particular course is electromagnetic field theory. So from that and some basic vector algebra, some very basic questions. So I hope you might have already attempted this assignment 0, and I found in the discussion forum some questions. Somebody had asked a question on this assignment 0. So I thought I would select a few questions from assignment 0 and we could just quickly solve them, so that if you have any doubts you could ask them. But maybe these are very simple questions, so we will just take a quick recap of this. So the very first question, the two given vectors A and B, if A dot B is equal to 0, the angle between the vectors is. So this is a very simple question. I think maybe you can just type in which among the following you think is the right option for the first question. Yes, I got one answer. So let me just tell you, A dot B, the vector A dot B is modulus A into modulus B cos theta. That is, the theta is the angle between vector A and vector B. So as per the question, this has to be equated to 0. Modulus A or modulus B cannot be 0 because those are magnitudes of the vectors. So cos theta has to be 0. That means theta is 90 degree. So the angle between the vectors is 90. So this is a very simple question. I think I don't need to explain more. But if at all any confusions, please do ask in the chat. But otherwise, I'll move to the second question. So the second question is, you are given with two vectors, vector A and vector B. And you are being asked to find the unit vector perpendicular to both vector A and vector B. Okay. So how do we find the unit vector perpendicular to vector A and vector B? Unit vector is A cross B divided by modulus of A cross B. So we need to find what is A. To find this, first you have to do A cross B. For that, AX, AY, AZ. So it's a cross product. As you all know, the second row should be vector A. Vector A, which is 1, 1, 0 and minus 1. So I am looking at the vector A expression and I am writing 1, 0, minus 1. And vector B expression 1, 1, 0. So I hope this is clear. This is very simple. So AX cap into 1 minus AY cap into 1 plus AZ cap into 1. So the final answer for the unit vector will be AX cap minus AY cap plus AZ cap divided by modulus of vector A cross B. Can you tell what is modulus of A cross B?
Under root 3.
Yes, under root 3. So that will be, I think, among the options, AX minus AY plus AZ by root 3. That is option B. So these are just quick recap questions to just based on basically the prerequisite. So the third question, so this was one question wherein somebody had asked in the discussion forum, the component of vector A along vector B. So this is, how do we find a component of a vector along another vector? So that is by taking dot product A dot B into B vector. Okay. So to do that, what you do is you have to find A dot B. Can you tell what is A dot B here? Looking at the two vectors, can you tell what is A dot B? Multiply AX, AX, so that is
0.
2, and AY, AY, that is minus 2, that
Hmm.
becomes
minus
0.
2.
Yes. So there is no component of the vector A along vector B. Okay. So that is option A. Now we'll move on to the next set of questions. So these assignment 0 is not considered for evaluation. That is the reason I am just discussing this straight away. So coming to the tangential sixth question, tangential component of electric field is 0 on a perfect conductor. So is it a true or a false statement? This is something which has been studied in electromagnetic field theory. Basically the boundary conditions at a conductor interface. Can you tell what do you think, true or false? Is it a true or false statement?
It's true.
Yes. So the tangential component of the electric field is 0 on a perfect electric conductor. Yes, it's a true statement. So it is, if you have any doubts, please refer to the boundary conditions in electromagnetic field theory. So coming to the next problem, which is basically a numerical, let us try to understand that. The electric field component of a plane wave traveling in free space is given by, so you see the electric field equation is given. Which one of the following is not true? Okay, so there are a few statements in A, B, C, D, and you need to see if it is true or not true. Okay, so the very first statement, let us see that. From the equation, can you tell the wave travels in X direction or not? Any
Yes,
idea?
Yeah, it's
Is it traveling?
The wave,
So let us see, is it traveling? The wave travel. So you are given with an electric field equation which says that electric field has an AX component. Electric field has an AX component. But how about the wave travel? How about the wave travel? That is very important. So the direction of wave propagation is not same as the direction of electric field. That is, that I think you might be remembering this from the electromagnetic field theory. We have electric field vector cross product with magnetic field vector, which gives a pointing vector, which is basically indicating the direction of the power flow. Okay, so basically the direction of propagation of the wave vector is nothing but this pointing vector direction. So I am saying that this electric field is in x direction. So the wave propagation is not in x direction. But looking at the equation, you can understand. So this is of the form. So if you look at this equation vector E is equal to E naught cos of omega t minus beta z. Okay, into Ax cap. So this Ax cap means electric field is in the x direction and the wave vector or the traveling of wave is in the direction of plus z. Okay, so if it would have been omega t plus beta z, then the wave travel is in minus z direction. Okay, so the wave travel is in z direction. So can you tell what will be the direction of this magnetic field? It must be y direction. So because Ax cross Ay is Az. So the first statement, is it true or false? So this is evidently false. So now coming to the second question, magnitude of electric field, is it 5? What do you think, is it true or false? Magnitude of electric field. Yes, it is true. Because as you see the equation, this is the equation for electric field. So the magnitude is nothing but this E naught, which is 5. And the unit is volt per meter. So the electric field is in volt per meter. Now coming to, so this is a true statement. Coming to the third option, the value of beta. Okay. Coming to beta, what is beta? Can you remember from the notation what is beta?
beta is the propagation constant.
Yes. So to be specific, we say gamma is the propagation constant, which has alpha plus j beta, wherein alpha is the attenuation constant and beta is the phase constant. Okay. So this beta phase constant, hope you might be remembering, can be expressed as 2 pi by lambda. And so from this equation, so there is one more parameter, like here if you look at this expression, this is of the form E naught cos omega t minus beta z. So omega is 10 power 7. So from that I can write 2 pi f is equal to 10 power 7. Or I can write 2 pi into f can be replaced by c by lambda is equal to 10 power 7, where I can find lambda is equal to 2 pi into 3 into 10 power 8 by 10 power 7. So what is lambda here? Can you tell what is lambda after simplification? Can you please calculate what is wavelength? Hope I am clear. So from the frequency, you find out the wavelength. That's it. Hello?
Yeah, 188.49.
Okay, that 60 pi you have multiplied, and I think yes, 60 into pi you have done, right? Yeah, 188. Yeah, yes. So this is basically 60 pi. So that is the last option. Wavelength is 60 pi. So that is true. Now coming to beta. What is beta? I have already given you the expression 2 pi by lambda. So let me write 2 pi by 60 pi. So what is beta value?
1 by 30.
Yes, 1 by 30. So this option C is also true. So what is not true is only option A. So the wave travel direction is plus Z, not the X direction. So I hope this question is clear. So this question had given a very basic understanding of the equation of electric field, and from that what all you can calculate. I hope this is clear. So moving on to the next question. If the electric field component of a plane wave traveling in free space is given by, so this is the expression for electric field, the average power density vector is given by. So you have an equation for electric field. Can you find the average power density vector? For that, what I told in the previous question. So you can write Poynting vector P as E cross H. Okay. And you also know that the impedance eta is basically modulus E by modulus H. Okay, intrinsic impedance is the ratio of mod E to mod H. Now, if you want, I can write H as E by eta, mod E by eta. So now, coming to the equation of average power density vector, this is from electromagnetic field theory, half into real of E cross H. Okay. So this can be expanded as E into E by eta, that becomes E square by eta. So I can write E naught square because it's a magnitude. Now eta can also be written as root of mu by epsilon. Okay. If it is in free space, I can make it as mu naught by epsilon. So E naught square by 2 root mu naught root epsilon naught. So average power density is E naught square by, into root epsilon by 2 root mu naught. Now I have mentioned only the magnitude. How about the direction? So as you know, the direction of electric field is AX. Direction of wave propagation is plus Z. So the average power density will have the same direction of the wave propagation. Okay. So that is plus AZ. So if you see, the option will be option D. Any doubts in this?
No, ma'am.
Okay. So let us then move to the week 1 content. So I would like to give a short brief. I hope you might have already watched the video lectures. So basically there were 4 lectures in week 1 content, based on which there was this assignment 1 which has to be submitted on I think 9th of August. So the very first lecture is on introduction to microwave engineering, wherein you have seen what is the frequency range of the microwaves, what is the history. As I told before, microwave started with basically radars and the application of radars in defense area and all those things. So the history, if we look at the microwave engineering history, it is from the basically from military and radars. So, but what we right now want to focus as the fundamental is the microwave transmission lines. So this is really useful. Because from the very basic coaxial line towards the microstrip lines, the fundamental concept of transmission line is same. So understanding this transmission lines is really very important. And then the very important parameter model, the circuit model which you have seen is the lumped circuit model. So I hope you have got the idea of what is this lumped circuit model. I think there was a question in the discussion forum again about the lumped circuit model. So hopefully you remember this transmission line. And so this is your source, and this is your source impedance, and this is your load impedance, and you have a transmission line of some length from here to here. And you see this is the current at any point on the transmission line at any time. So this current, that is why it is dependent on 2 parameters, I of ZT, and voltage is again dependent on Z and T. So Z is the spatial location, T is the time. So if you look at a small portion of this big transmission line, which is represented by delta Z. Okay, so you have a long transmission line for which we are just considering a small section or the infinitesimal section of the transmission line. So that can be represented as this particular lumped circuit model. Okay, so which consists of the primary constants, which is R, L, G and C. Okay, so this is the lumped circuit model which has been discussed. So, and you know the relevance of each of these parameters: resistance, inductance, leakage resistance, and that is nothing but the conductance, and then the capacitance. So this can you tell why this capacitance exists in a, say for example, in a coaxial line? So coaxial is basically, as you all know, that is a center conductor and an outer conductor. So where does this capacitance come into picture in case of a coaxial line? Or why there is a capacitance?
Sorry, ma'am. Can you repeat again?
So my question, I think you did not understand my question. So there is, all of you know about a very common transmission line, which is a coaxial conductor, which consists of basically 2 conductors, inner conductor and an outer conductor. And you all know that there is a dielectric between these 2. Okay. So can you tell where is the relevance of this capacitance in this coaxial line?
Between 2 conductors.
Yes,
Where
exactly.
the dielectric is.
Yeah, yes. So you all know the concept of capacitance. Between 2 conductors, you have a dielectric, then there arises a capacitance. So similarly, you have come across what is the relevance of inductance. When there is a current flow, there is a magnetic field change, and then that causes a inductance and at the same time resistance, and also a leakage current which contributes to this conductance. So I'm not going into the details of these, just wanted to give a idea of what is the lumped circuit model. So this was all about the first lecture. Coming to the second lecture, you had the transmission line theory, where you have derived the telegrapher's equation, and you have also come across the wave propagation on the transmission line. So the wave equations. And the very important thing to discuss here is what is the lossless line. So as I discussed here about the lumped circuit model, can you tell what is the definition of a lossless line, or what happens in case of a lossless line?
Ma'am, in lossless
Exactly.
line, R and G will be 0.
Yes, exactly. So that is your lossless line, and with and without termination. So in this case, you have, if you have a termination, ZL or not, that is the other thing. So these kind of, so in a lossy transmission line, you will have so you will have losses, that is R and G are present, and you might have also come across something called as distortionless line. I hope you remember the condition for a distortionless line. Just to give an idea, in a distortionless line, R by L is equal to G by C. So whichever line follows this condition is called as a distortionless line. And towards the last lecture of this week 1, we had a discussion on the Smith chart also. In Smith chart, there is this resistance circles and reactance circle, R circle and X circle. So all of you are familiar with this. So just to give this, these are all called as R circles, okay, and these are called as the X circle. Okay. Now, and I hope you remember how to plot an impedance. Say, for example, if you have a normalized impedance, say this is like load impedance. For example, if you have something like 50 plus J 100 or something like that, and your characteristic impedance is say 50, then the normalized impedance can be taken as ZL by Z0, which will be 1 plus 2J. Okay. So how do you plot this? So find out the R circle, which is basically R is equal to 1 circle. Okay. So here from this, the idea is R is equal to 1 and X is equal to 2. So plus 2. So that is very important. That is very important. So R is 1. So you have to find out an intersection point of R equal to 1 circle and X equal to 2 circle. So R equal to 1 and X equal to 2. So this is the intersection point and this is the load impedance which is being plotted. So just giving all short introductions of these, let us move on to solving some problems. So these are some sample numericals. Let us try to solve it, and I suggest you try to solve it with me so that you can give the answers. So we will try to, I'll try to explain the question and you can try solving the numerical, and then we will discuss the final answer. In a lossless line, the phase velocity is 2.8 into 10 power 9 meter per second. The characteristic impedance of the line is 50 ohm. The capacitance per unit length. Okay, so that is being asked. So how to solve this? So the very basic clue is it is a lossless line. So if it is a lossless line, what is the expression for Z0? So
Under root L by C.
Yes, exactly. So the basic expression is root of R plus j omega L by G plus j omega C. Because it is a lossless line, R and G become 0 and the expression reduces to root of L by C. Now, what for the phase velocity. Phase velocity is omega by beta. So
1 by under root LC.
Yes, beta can be written as omega root LC. So this will be 1 by root LC. So if you multiply Z naught into Vp, root of L by C into 1 by root LC. So root L and root L gets cancelled and 1 by C. So can you evaluate C from here? Yes, you can. 1 by Z naught into Vp. Can you please quickly calculate and tell me the answer? Remember, the capacitance unit is picofarad per meter.
$7.14.
I couldn't get you.
7.14.
Okay.
Picofarad.
So option C. Yes. So option C is the right option. Z naught is 50. 50 into 2.8 into 10 power 9. So if you solve this, you will get it as 7.14 into 10 power minus 12 farad per meter, which is basically picofarad per meter. Hope this is clear. Then let's move on to the next question. Okay, before discussing this question, I would like to show an illustration. I hope this is visible.
Yes.
So the idea is to talk about standing waves. So all of you know what is standing wave. So this is a short animation of what is this standing waves. So you know that from the source towards the load, there is a forward power. And if the load impedance is not matching to the characteristic impedance of the line, then there will be a reflected power. Okay. So not all power is fed to the load. That is the situation. So in that case, you have two waves. One is a forward wave and other is a backward wave. So these two just get interacted together, interfere together, and that creates a standing wave. So just to have a, so this is the forward wave. So maximum transfer occur when the characteristic impedance is equal to the load impedance. Now, suppose if you have a unmatched, that means say for example, if you have a short circuit at the load or open circuit at the load, you will have this two waves interfering with each other. So those interference will create the standing waves as seen here. Now I would like to talk separate cases. Okay. So, okay. So, before going to the question, I just wanted to give idea of what is the how the standing wave pattern look like in each of the cases. Okay. For example, if you have a matched line, that means Z not equal to ZL, you will have a you will not have a standing wave pattern because there is no reflection if there is a matched line. Okay. So in that condition, you have a constant voltage. Now, say for example, if your load is basically short circuit in the sense ZL equal to 0. So if it is a short circuit, so what happens at a short circuit, all of you know that this voltage at the load end is 0. Okay. So this voltage, I mean the voltage waveform will have a minimum. Okay. Voltage waveform will have a minimum at the load end. Okay. And if you look at the open circuit line, that means when the ZL is infinity, you can see that all of you know that the voltage is maximum but current is 0. Okay. So your voltage will be, so there will be a V max at the load end. So this is basically representing the load end. So at the load end, in case of a short circuit, V max is, sorry, V min, there is a V min. And in case of an open circuit, at the load end, there is a V max. So this is a V min, whereas this is a V max. Okay. So these are special conditions: matched line, short circuit line, and an open circuit line. What happens if it is like the load impedance RL is slightly greater than the characteristic impedance, or if slightly less than RL less than Z0 and RL greater than Z0. Okay. So these are the two conditions which I would like to discuss now. So if you see, so the dotted line here is the current waveform and the solid lines are the voltage waveform. So you can see that at the load end, voltage is minimum. So there is a V min. And in case of RL less than Z0 and in case of RL greater than Z0, voltage is maximum. So this is clearly evident because you all know that whenever RL is greater than Z0, there is a voltage there will be a high voltage across the load because load resistance is greater than the characteristic impedance. Okay. So this is some clue which you have to keep in mind such that you can solve the next numerical which I wanted to solve. So look at this question. A lossless line of characteristic impedance 50 ohm, so that is Z0 equal to 50, is terminated in a load resistance 75 ohm. Okay. So as you know, understood, so here it is condition is like ZL is greater than Z0. So obviously, so if this is ZL on a transmission line and this is Z0, at the load end, you have a V max. Okay. Frequency of operation is 1 gigahertz. So you are given with the frequency of operation as 1 gigahertz. And phase velocity on the line is 2.4 into 10 power 8 meter per second. Location of the first voltage minimum from the load is. So if you have a voltage maxima and so all of you know about the standing wave pattern. So this is called as a V min and this is called as a V max. So the distance between a V max and V min, can you tell what it will be?
Lambda by 2.
So this is a so this is a half wavelength. So this will be a lambda by
4.
4. Okay. So I am saying, so as I told before, whenever load impedance greater than characteristic impedance, at the load end you have a V max. Okay. So at the load end you have a V max. From the load at some lambda by 4 distance, you will definitely have a V min. Okay. So if this is V max, from there lambda by 4 distance, you will have a V min. Okay. So the idea is to calculate this lambda by 4. Now, how do I calculate that? I need to know what is lambda. So to get that lambda, you need to solve this. Lambda is equal to 2 pi by beta. So, any idea what can be replaced for the beta?
Yes, ma'am. Vp equal to omega
Yes.
by beta. Beta
So,
will be
yes.
omega by Vp.
Yes, you are given with the frequency of operation and Vp. So obviously you can replace it as omega by Vp. So 2 pi by 2 pi f. Here Vp will come here. So finally you can write it as Vp by f. So Vp is 2.4 into 10 power 8 by f is 1 giga 10 power 9. So you get an answer 0.24 meter. So this is wavelength. Okay. So wavelength is basically 24 centimeter. So our answer is, lambda by 4. So 24 by 4, 6 centimeter. So that is the location of the first voltage minimum from the load. So at the load end you have a voltage maximum. From there lambda by 4 distance you have a first voltage minimum. So hope this is clear.
Yes, ma'am.
Okay. So we'll move on to the next question. Okay. So this question is on VSWR. So probably you remember the expression for VSWR. So suppose if you know let us say you have a reflection. So whenever there is a mismatched load, there is reflection, and that reflection coefficient is written like ZL minus Z0 by ZL plus Z0. And from that, we also came to the expression for VSWR, which is 1 plus mode gamma by 1 minus mode gamma. And so if you rewrite gamma, the reflection coefficient is rho minus 1 by rho plus 1. Okay. So based on this question, you see if the VSWR on a lossless transmission line terminated to a load is 4. So rho is 4. Fraction of incident power transferred to the load. So we want to know there is a Z0, there is a ZL. Some power is getting transferred to the load. We want to know how much is that. The fraction of incident power, what fraction of an incident power is getting transferred to the load. So what we know is the reflection coefficient. That is basically voltage reflected to voltage incident. Okay. So if we take the square of that, what you will get is power reflected to incident power, the ratio of reflected power to the incident power. So that is your gamma square. So 1 minus mod gamma square will be, so say this is gamma square. So I can say this is like reflected power. So 1 minus mod gamma square will give me the transmitted power. Okay. So from rho, I can calculate gamma. Can you please tell me what will be the value of gamma?
3 by 5.
Yes, that will be 3 by 5. So gamma square will be 9 by 25. So 1 minus gamma square, that is the fraction of incident power, transmitted power to the incident power. Okay. So that is 1 minus 9 by 25, which is 16 by 25. Hope this question is clear. Okay. So moving on to the next question. So this is a question from distortionless line case. So just to refresh the concept of distortionless line. So if you remember, the condition for distortionless line is R by L is equal to G by C. And under this condition, what is alpha and beta? Hope you might have gone through the lectures and you know this. R is equal to root of C by L and beta is equal to omega root LC. Okay. So this is the condition for distortionless line, and under these conditions, alpha and beta get reduced to these equation. Now, we know that the propagation constant is alpha plus j beta. So here, if you look at this, alpha is basically frequency independent and beta is frequency dependent because beta has a parameter omega. Beta is dependent on omega. So what we have here is the attenuation constant. A distortionless line has an attenuation constant 0.002 and the unit is Napier per meter. And the resistance per unit length is also given. So from the expression alpha is equal to R into root of C by L. Resistance per unit length is R, 0.1 ohm per meter. What you want to find is the characteristic impedance. So can you see this relationship here? What is root of C by L? That will be written as R by Z naught because Z naught is root of L by C because it is a so we can write this R by Z naught. So here I can write this as Z naught and Z naught will be 0.1 divided by 0.002. Can you tell me the answer for this? Option A, B, C, D. Among the options A, B, C, D.
50.
Yes, 50 ohm. Okay, now let's move on to the next question. So in this question, so basically I have shortly described you about Smith chart. I hope that is very basic to all of you. Consider a load impedance ZL is given 50 plus J50. Normalizing the impedance with respect to 50 ohm. The radius of resistance circle passing through the load impedance point on the Smith chart is. Okay. So what is the normalized impedance? Actual impedance divided by Z naught. So 50 plus J50 divided by 50. So this becomes 1 plus J. So this is the impedance point. So if you remember on a Smith chart, 1 plus J. So 1 plus J. So this is the R equal to 1 circle and this is the J equal to 1 circle. So the intersection point is this one. And this will be the ZL. That means the normalized impedance. Now the question is about the radius of resistance circle passing through the load impedance point. What is the radius of the resistance circle? Remember, R equal to 1 doesn't mean that the radius is 1. So there is an expression for the resistance circle equation, that is omega R minus RL by 1 plus RL the whole square plus gamma I square is equal to 1 by 1 plus RL the whole square. So this is an equation of a circle with center this one, and this is the radius. You all know the equation of a circle. So this radius will be 1 by 1 plus RL, where RL is your RL plus JXL. So here you know RL is 1. So 1 by 1 plus 1, which is 1 by 2. So the answer is option B. So this resistance circle equation has been described in detail and derived and all that in the video lectures. You can refer to that. Hope this one is clear. Moving on to the next question. A lossless transmission line of characteristic impedance 50 ohm is terminated to a load resistance of 100 ohm. Return loss in dB is. So here you need to just have an idea of what is return loss and what is the expression for return loss. So as usual, you know what is Z0 is 50 ohm and ZL is also known to you 100 ohm. Can you calculate the reflection coefficient here? Can you please tell the answer for reflection coefficient? ZL minus Z0 by ZL plus Z0.
Its final answer is 13.98.
Yeah, final answer is 13.98. Okay. So this is 100 minus 50 by 100 plus 50, which gives 50 by 150, which is 1 by 3. So the expression for return loss is minus 20 log of gamma. Okay. So if you know this is very simple to solve. So minus 20 log of 1 by 3. Sorry, Anup, the right answer is not option B. 20 log 1 by 3 is, can you calculate again?
Oh, okay, ma'am.
Yeah. So 20 log 1 by 3 is 9.54 dB. Okay. So that's
Oh,
all.
9.54.
Yeah,
Sorry, ma'am.
9.54.
By
Yeah,
mistake,
yeah.
I press another number.
Okay. So, this parameter return loss is quite familiar to people who have come across antennas, wherein you see that we look at return loss rather than reflection coefficient. I mean, the technical parameter generally used is return loss. Say, for example, you have an antenna which transmits at a resonant frequency of 1 gigahertz. Say we look at the characterization and we see that there is a dip. I mean, the return loss is, we see that the return loss is less at its particular resonant frequency. In case of an antenna, we want to transmit maximum without having any reflection. Okay, maximum transmission to the free space or whatever. So with reflections as minimum. So that is why we do the impedance matching. So for that, the reflections should be minimum. That means the return loss, we have to have a larger dip in this. That so the antenna is as efficient as antenna will have a minimum reflection at that particular frequency. That is something which you, if people have worked on antennas and such areas, you would have already come across this particular term, return loss. Okay, coming to the next question. The input impedance of a given length of a lossless short-circuited transmission line. So please remember what is here. A short-circuited transmission line means ZL is 0. The load is shorted. Now, and the impedance is 50 ohm. Z naught is 50 ohm. And the input impedance is J 50 root 3. Okay. So, to make it very simple, the load end is short circuited. You have a characteristic impedance, and I'm saying that at some location, the Zin is J50 root 3. Okay. Now tell me what is this length of the transmission line. Okay. So that is the question. For this, you need to have the understanding of a short circuited transmission line, for which the expression for input impedance is derived as J Z naught tan beta L. So once if you know this is easy. So just substitute J50 root 3 is equal to J50 into tan beta L. J50 gets cancelled. Tan beta L is equal to root 3, whereas beta L can be written as, what is beta L?
Beta equal to pi by lambda into L.
Yes. So beta L is pi by 3. So 2 pi by lambda into L is pi by 3. Pi gets cancelled. L is equal to lambda by 6. Okay. So for a length of lambda by 6, the input impedance becomes J50 root 3 if the load is short circuited. So what if the load is open circuited? What is the expression for input impedance? Any idea?
Sorry, ma'am.
Say for example, instead of short circuit, if it was an open circuit, I mean the ZL is infinity. In that case, what is Zin? Expression for Zin?
Expression for
J Z naught code beta L. Okay. So these were derived in the video lectures. Hopefully you would have noticed it. So these are very basic understanding of transmission line. So in case of a matched line, in case of a short circuited line, in case of an open circuited line. These are three important special cases of a transmission line. Coming to next question here. I think I have one more this question. Meanwhile, I would like to ask if you have any particular doubts or questions. I mean, in general, about the week 1 content or any of the. Okay, Anu, please go on.
Then I know the Z naught, that is the characteristic impedance of a lossless line, and uh, another one is distortion left line. Distortion left line. In both lines, there is no any J, or you can say that this is independent from imaginary. So, but why we consider only distortion left line as a pure uh, real number? Why we not consider lossless line as a real number?
Real number in the sense, are you talking with respect to the impedance?
Yes, ma'am. Z naught.
Z naught. Okay. Z naught is root of R plus J omega L by G plus J omega C. It need not be real always.
No, ma'am. This is imaginary now, but if I consider lossless line, then
Yes.
R and G will be 0 and
Yes.
V gets under L by C.
Yes.
Okay. And if I consider distortionless line,
Yes.
then I got Z naught equal under root L by C.
Yes.
So why we consider only distortionless line characteristic impedance of distortionless line real number? Why we not consider for a lossless line?
Mm, I think I'm not understanding your question. I just let me know if I am right with respect to your question. So you are saying that in case of lossless line, R and G are 0. So I can write Z naught equal to root of L by C. In case of a
Yes.
distortionless line, R by L is equal to G by C. So are you asking a question? In that case also it is root of L by C. How? Or something else? Hello?
Yes, ma'am. Yes, ma'am.
So are you asking why Z naught is real in case of a distortionless line?
Hmm. Mm-hmm. Exactly.
Okay. So in that case, so if you have gone to the derivation of distortionless line, you have to uh, see the derivation how it has come to root of L by C. So you apply this condition here in this expression and simplify it and see that it is root of L by C. It reduces to root of L by C under certain conditions.
Yes, ma'am. I
So,
know.
okay. So in both the cases, it is, so in this case, yes, it is, see, there is no ideal line wherein R and G are 0. So so it is like an ideal condition. So for simplification purpose, we just look at this expression. If there was no loss at all, then what happens to the line? So in that case, we derive this lossless transmission line. But practically all lines will have at least some losses. Are you getting my point?
No, ma'am. Can you repeat it again?
Okay, so if you see, if you remember the line, okay, so you have a, say for example,
Ma'am, ma'am, if I see only formula, then why we not consider lossless line as a real impedance or real characteristic impedance?
lossless line has a real characteristic impedance.
But ma'am, in previous assignment, or you
Hmm.
can say in this particular assignment,
Okay.
uh, yes, ma'am, this is not an option.
Okay, maybe it is a tricky question in the assignment. I think you got confused with that statement. Uh, so, are you talking about the characteristic impedance of distortionless line? It is real or
Ma'am,
complex?
ma'am, one second. I send you screenshot in a chat box.
Okay. Or there were some interactive questions. Is that pertaining to that? There were some questions like true or false.
Exactly, ma'am.
Okay, okay.
Ma'am, there is no any option to send any photos.
Okay, okay, that is fine. So is it related to the self-assessment questions in each lecture?
Yes, ma'am.
Okay, so there is a question something like this: characteristic impedance of a distortionless line is real, true or false?
Exactly, ma'am.
Ah, yes. So under what condition that becomes real? So this is a question. So it is like, for a lossless transmission line, the characteristic impedance is always real. Is it true or false? Okay, Anup, you can do one thing. I am
Yes, ma'am.
just typing in my email ID. You can
Oh, okay, ma'am.
send me the screenshot of what you are asking.
Oh, okay, ma'am.
Okay, I because I am unable to catch what you are asking. So I'll
Ma'am,
reply.
if you allow me, then I can present.
Okay. Okay, just a month.
Ma'am, my screen is visible.
Yeah.
So, ma'am, this one is one second. This one. And this is the question. If the characteristic impedance of a transmission line is real, the
Hmm.
line has to be lossless line. If then here I click
Hmm.
true, then the answer is false because the accepted answer is false. Why? Because then it is
Okay,
real
okay,
now.
okay. See, this is a tricky question. If the characteristic impedances of a transmission line is real, can you project it once again? That statement is.
Sorry?
Can you project it once
Oh,
again?
okay.
Can you present it once again?
Yeah. Yes, 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 yes. Hello.
One minute, 1 minute.
Okay.
So the statement says if the characteristic impedance of a transmission line is real, the line has to be lossless line. Is it mandatory that line has to be lossless line? So it is a kind of tricky question wherein they have asked, uh, is there any other line on which the characteristic impedance becomes real? You got
Yes,
my
ma'am.
point? So
Yes, yes, yes,
if
ma'am.
somebody asks you like it is always in this case only, so then it is
Okay.
true or it could be false. You find out where it is. So this is a question in the assignment also, so I don't want to straight away discuss that. So I am trying to tell you, for a impedance, that means for the characteristic impedance to become real, is it mandatory that it should be a lossless line? Is there any case that any other line also can have a real characteristic impedance? That is the meaning of the question. Okay.
Okay, okay, okay.
Okay.
Okay, ma'am.
So you just rethink about that. Okay.
Okay, ma'am.
Okay.
Okay, thank you, ma'am.
Thank you. Anybody else has any particular questions or doubts? I think I have one last question to discuss. So for a transmission line, RLGC and Z0 is given. So these are the primary constants and Z0 is the characteristic impedance. So there is a condition given here. R much less than omega L, G much less than omega C. Which of the following expression represents alpha? Okay. So let us look at the condition. R much less than omega L, G much less than omega C. So R into G, if I take the product, it is much less than omega square LC. Okay. Now let us look at the expression for gamma. We know the propagation constant gamma is root of R plus j omega L into G plus j omega C. Now, suppose if I expand, so R into G plus j omega L G plus j omega RC minus omega square LC. So this is pure expansion. Okay. Now in this, I want to take this particular term omega square LC outside. Okay. I am trying to simplify, that's all. So omega square LC, I am trying to take it outside the square root, so that becomes j omega root LC. And under square root, I will have, so the first term is RG. I wanted to divide by the term omega square LC. So RG by omega square LC plus j omega LG by omega square LC, j omega RC by omega square LC minus 1. Sorry, plus 1. Because we took minus omega square LC outside. So here everywhere I have the minus. Okay. Now simplifying this, j omega root LC into root of 1 minus. So if I simplify this, I'll get. So if you look at this first term, based on our condition, R into G much less than omega square LC. So in that condition, this first term goes to 0. I mean, it can be neglected, ignored. How about the second term? It becomes omega. So minus j, I'll take it outside. L gets cancelled. G by omega C minus second term, it becomes C gets
I
cancelled,
think it will
R by omega L. Okay.
then it will be plus, I think, in bracket.
Which one? Oh, yeah. This is plus. Yeah. So now, if you look at this expression, gamma is alpha plus j beta. So alpha is a parameter which is real. So from this expression on the right hand side, if you expand, which is real, okay? So you will get a real term when you multiply this j with j, okay? So if I take out that real expression, that will be 1 minus j by 2. Sorry, alpha is equal to did I miss a 1 by 2 somewhere? I think. Okay, just a moment. So this expression, it is like root of 1 minus x. So you know that root of 1 minus x is nothing but 1 minus x the whole raised to 1 by 2. Okay. So using binomial expansion, if you expand this one, that will be 1 minus x by 2. Neglecting the higher order terms, this becomes 1 minus x by 2. So similar way, if I try to expand this root of 1 minus that parameter, I will get 1 minus j into g by omega c plus r by omega l whole thing raised to half. Okay. So then it becomes 1 minus half into so and so. Okay. The binomial expansion. Then if I take only the real parameters, that becomes half into r into root of c by just a moment. So we'll try to expand it here. J omega root LC into 1 minus j by 2 into r by omega L plus g by omega C. Okay, so this is your gamma, which is alpha plus j beta. So this is after expanding for the binomial expansion. So if you multiply these two, you will get omega root LC multiplied by 1 by 2 into r by omega L plus g by omega C. So if I expand it, that becomes omega gets cancelled. So half into r root of c by root L plus again multiplied by the second parameter, it becomes g root c root L. Okay. And you know that root of L by C is Z naught. So I can write it as, so this is basically alpha. Only alpha I am expanding because the question asks only for alpha. R in R. So root of L by C. So R by Z naught plus G into Z naught. So this is the expression for alpha. So this in the options, it is R by Z naught plus G Z naught. Option B. So the idea is you expand the expression for propagation constant, apply the conditions. If required, expand it using the binomial theory of expansion, and then you can simplify and get the expression for alpha, or you can also get beta. Now, in this question, it is only asked for alpha. That is why we looked at only alpha. So that's all for today's session. If you have any questions, you can ask. I would suggest you to interact, and at the same time, if you have any doubts, you can put in the discussion forums. I'll be looking at that, and I'll try to look at the discussion forum before the session, and we'll try to um, include those questions in our weekly sessions. And if you have any feedback, please feel free to tell, so that I can incorporate in the sessions. Thank you.
Thank you, ma'am. It was very clear and very nice session.
Thank you. Thank you. I
All doubts
hope
got clear.
all of you keep the spirit of continuing the course, because most of the time, towards the end, there will be a lot of things which you might be expecting to look at. So keep the spirit up, so that you will have a continuous, the continuity for the course, and you try to complete it. Thank you. Thank you, Arun. And thank you,
Thank you.
Suvarna. Thank you, Anup.
Thank you, ma'am.